Awesome. Let's get started then. Okay, so thank you so much everyone for joining me today. We're going to go over an introduction to machine learning. And I think this will be a very important aspect as you go through your coding competition throughout the day. So make sure you pay attention. And also don't worry, we will share the slides with you, so you won't need to write anything down unless you think it's really important. Okay, let's get started. Okay, first of all, let's start with artificial intelligence. What exactly is artificial intelligence? Well, artificial intelligence is the ability for a computer to make decisions similar to a human. So think of it as your computer making decisions that you would make every single day. What should I wear? What's the best dress for the weather outside? Or what color is my car? Or what's the best price for a house to buy at? All these decision-making aspects are something that artificial intelligence can help us create that computers normally couldn't before 20 years ago. It's important to realize that artificial intelligence helps us create computers, helps us function with computers in ways that we couldn't before. If you ever had any phone, then you've already used artificial intelligence in your life. Now let's talk about machine learning. So machine learning is a branch of artificial intelligence. However, machine learning focuses on an ability for a model, which we'll talk about later, to learn. Now this model learns from an input data, which once again we'll talk about later, and it allows us to create an output. But it heavily relies on data and algorithms to learn and solve, or even learn even more. It's important that we learn more about data because our data will help our model create much better output. And we want an accurate model in order for our machine learning to be the most accurate possible and be the most useful data possible. So let's talk about examples of machine learning. We have the Google search algorithm, where it's a complicated matrix that allows us to search up between words and give you the best output. So if you've ever used Google and you always see the time that it gives you when you search something up, just remember that Google is just showing you how fast its algorithm works. And it's actually impressive to think that in the wide range of databases that Google has, it gives you the search output within milliseconds. And make sure you take that into account next time you search something up, or even when you search something up and it becomes really close to what you want. For example, in computer science, if you were to search something up and you go to Western University, Google would give you the Western computer science specialization instead of some other university. Another example of machine learning is the Instagram algorithm. So the Instagram algorithm has been changed over the past couple of years, but it gives you your feed based on the most activity. When your activity is interacted with different users, liked or commented, then it posts to even more users. But let's say that your photo isn't as good as it should be, then the Instagram algorithm will take it away and will bring less and less users, eventually shutting it down from the feed overall. Also, we have the Tesla Autopilot system. I'm sure all you guys have heard Tesla all over YouTube and all over the news, but the Tesla Autopilot system learns through its own data. It records millions and millions of miles driven, and it takes all these responses, all the errors, and learns from it once more. I believe we're in full self-driving mode around now, but it's cool to see how far it's come even all the way back in 2012. Next time you look at a Tesla, just remember that there's a lot of processing going on in there in order to allow it to roll over through the roads. I believe it's something like 2 million processes per second. And finally, Siri. Like I said before, if you use a phone, then most likely you've used Siri. And Siri is all about machine learning. It learns your different features. It learns what you want. It learns what you want to put. For example, if I ask Siri to put in a task, it will learn what the task is and even what time to put, or even an estimate of the duration of it. These are all stuff that we didn't have before. If you ever had the iPhone 4S and you used Siri on that, the Siri was pretty bad. I remember using it and asking it some questions like, how is the weather today? Or what will the weather be tomorrow? And it wasn't able to clearly learn it. However, now if we look at Siri, it's such a powerful device. And that's how the progress of machine learning has helped us through. Let's talk about the parts to machine learning. So first things first is we have the model. What exactly is the model? Well, the model is basically our feature. The model is basically a piece of code where the model will learn and through an input and give an output. The model is one of the most vital parts. It's the part that we'll interact with through machine learning. It's also important that our model is trained properly. We also have a set of algorithms. These algorithms are basically how the model will learn. Once you give it a set of data, what will it do with it? And this is exactly what the algorithm teaches it to do. When we run through different examples of machine learning today, we'll realize that these algorithms are really vital to helping the model learn perfectly. And the wrong algorithm can give you the wrong accuracy. An incorrect accuracy. Next up, the data set. So the data set is just a set full of all points that you have. So let's say that you're given 100 samples. What do you do with the data? And that is your data set. Whether you take 50% of that data and use it for something else, or 50% and 25, and split it in however many different ways you want, the data set is your most vital part of training your model. You want to make sure that you have the adequate data set in order to make sure that your model is most effective. And adding on top of that, we have a training and testing set. The training allows the model to be trained through the training samples, and the testing set allows the model to be tested in terms of accuracy or scoring, in terms of whatever we have, where we compare the testing Y value into the predicted value of the model. And finally, feature extraction. If you have a model that gives you 5 different features, for example, the color of a car, the size of the tire, or many other different examples, all those features may not be as important to the speed of a car. For example, the color of a car wouldn't really matter to the speed of a car. And that's why feature extraction is important. We want to make sure that we look at the right features in order for our model to be most effective. And these are the different parts to machine learning. Next up, we have the model. So going deeper into the model is basically what will receive the input and output and generate an output based on algorithms and training data. So we see the input coming in, and this box is represented by the model, but think of it as a big block of code that will keep processing data iteratively. And finally, it produces an output. And with this, it's sort of like your basic introduction to how the model works. We'll go more deeper into this and how to work and interact with the model so that you can produce an output similar to this. Let's start with regression. So regression is the correlation between data. If you in high school, we sort of did like a line of best fit, and this is sort of the same thing, where we want to make a line of best fit to the sample data that we have. We produce an output based on the training data. And the types of regression that we have is linear and polynomial. There's so many different more, but the two that we'll go through today are linear and polynomial, and also logistic. Another thing to note about regression is that the output is continuous. No matter what x value we put into it, we need to make sure that there will be a continuous y output. But also, all this y output the range of this output may not be applicable to all our situations. For example, if we're predicting the climate change and how the temperature will increase, in 1,000 years, it may not be as applicable because of the uprising trend. It may stop, or some things may change. So that's why it's important to note the scope of your variables and to know when exactly you want to choose your variables or what exactly we're going for. So what exactly is regression used for? As I gave the example of climate change, we also have house prices, the spread of diseases, or even the depreciation of a car. But note that these are all patterns. And that's one important thing to know about regression. There has to be a pattern in order for the model to be accurate. If you just give a cluster or a clump of different data points and they're all over the place with no specific pattern, then what's going to happen is that your regression model will not produce a correct output. And this will be very detrimental to your scoring ability because you won't be able to get the right pattern. And if you can't choose the right pattern, how exactly are you going to make a correct pattern? So make sure in your data set that there will be a pattern, and you can always just plot your data points, which we'll talk about later, and you'll see how the pattern you can create and choose a different type of regression based on the pattern that you see. So once again, the implication for a data with no patterns is that the model won't really produce the right output. And this will be very important to realize that like a model with no pattern is just data points all over the place, and the line would look really weird. Like the scoring accuracy would probably be less than 50%. So make sure that your data is adequate for your model. Okay, now let's start with linear regression. So as we know, a linear line is y equal mx plus b. But how does our model actually know what values to put in m and b? And this is what we're going to learn about later on. Is there a way that we can also find out how accurate our data is? As I keep mentioning scoring and accuracy, how do we use that in our actual test case scenario where we have our training data and our testing data? And finally, how do we visualize a model so that we get something like the bottom right? If we can't visualize our linear regression, then how do we know what exactly is going on? After all, we can sort of see the line of best fit in our heads, but how will we connect that to how the computer thinks of it? And that's how we can decide between visualizing data. Okay, now let's talk about the math behind it. So the math behind linear regression is that it's an iterative gradient descent. And gradient descent is basically it chooses between the two weighting points, which is W0 and W1. Going back to the equation before, this is just M and B. So we're just substituting with W0 and W1. And essentially these weightings are changed iteratively. So they add one or they add a different rate, and that depends on the learning rate. But essentially, once we go through each and every iteration process, we look at the cost function, which is sort of like the minimum error value, and we figure out what the best value is for this function. And that allows us to create the best weighting possibility for this. So something with a higher learning rate or something that iterates through every iteration, the W0 and W1 will go through a bigger jump, we'll see that it sort of misses through the optimal point. So the optimal point in this equation over here we see is in a parabola, and we're looking for the minimum loss, which is all the way at the tip. So a smaller learning rate will be able to go through this much more clearly because it'll be able to jump through smaller steps. However, that comes at the cost of computing power. So make sure that you don't turn up your learning rate all the way in case you think that it'll just get the right amount of value, because you can even give a lower learning rate and still get the same output because it comes at the cost of computing power. So as we look at the bottom left, we see that the convergence happens when we get the two different weightings and we assign them with different values. So once again, iterative gradient descent is used in linear regression, but can also be used in many different models. We essentially want to change the weighting until we find that optimal point for us. And that becomes very important as we try to figure out what's the best line. So as we look back, we might start off with a line that may look very different from what our model may be, but then our computer can realize through the error is that it may not be the best model. And that's where we iteratively start getting to the best model. Okay. Now let's go beyond more to the math of it. So I kept talking about the cost function in the error, and that's sort of the squared error cost. And it basically gives us the predicted value, which is h of xi. And what it does is it essentially gives us this value and takes the difference of it from the actual value. So if you look at the bottom right, we can see the dotted line error next to the line. So we take this error and we square it. And this is our cost function. The lower the differences, the lower the error and the lower the cost. We essentially want the lowest cost to get the best function. So keep that in mind as you look through your data. If your line is sort of all over, if your dots are not in line with your model or your regression, then you know that it's going to be a higher squared cost. So another thing to realize is that this data may not exactly be set for linear regression because we can see that the points are all scattered around. And that may be due to outliers or due to some other circumstances. So you can either take a look at different types of regression, or you can also take a look at different types of models, and that we'll talk about later. Okay, now let's talk about accuracy. So as we talked about before with training and testing sets, we know that between these two sets, it's really important that we make these two sets and split our total sample into these two different sets. When we have a training set, we can train our model and that can produce the right output. But we can't test with the training model because the model already knows what to do with the training values. That's how it learned through it. We're going to use a different set, which is called the testing set, and that will allow us to create a better sense of how accurate the model is. Essentially, these are points that the model has never seen before. Sort of like when you look through a test, when you're reading through it and you get a different question on the test. If you got exactly the same question each and every time on a math test, then you would know what to do. However, if you get a different question with different numbers, then that puts your knowledge to the test. And that's sort of what we want to do here. So we see if the model produces an accurate output from the actual value. So whatever model we predicted from Y, is that true from the testing set of Y? And that's how we determine the accuracy. And when we go through the example, I'll show you how to use that function in your model so that you can predict your score and see how accurate your model actually is. Okay, so now I'd like everyone to either go to the link or scan the QR code so you can take some time to go to this Google Colab notebook, and over there we'll go through a linear regression model. So I'll just give everyone a quick minute to load up, and then we'll get started from there. Okay, so if you haven't already, make sure you go to the link in the Zoom. That's where the link will be now, and that'll be to the Google Colab notebook. And make sure you keep that tab open. Okay, so let's get started. Here is okay, so this is our machine learning notebook. It consists of the title and then the 4 different sets that we'll go through. So what we're going to start with is the model plus linear regression. Okay. So first things first is, I'm sure you guys already went through the library workshop, but if not, we're basically going to import our libraries such as NumPy, Matplotlib, and Pandas. And this will basically be our data frame models. Also, we're going to import some things from sklearn, and specifically, we're going to import linear regression. This will basically be our linear regression model that we're going to fit and eventually test and score on. Another thing to note is that we're also going to be using a train test split. So you don't need to do it. You don't actually need to code it yourself. It already comes with sklearn, which is a very useful feature because I tend to use it a lot in my data. Okay, great. So once we're done with that, we go through creating and arranging the data. So this is sort of a made-up data set point, but essentially we have, I believe, 7 different points, and each consists of a different Y point. And what we're going to do is we're going to set that into a NumPy array. It's important that we set that into a NumPy array because that's how our linear regression model is actually going to learn from it. Okay, once we're done with that, we're going to put it into a train test split. So over here, we have 4 different variables: train, xtrain, xtest, ytrain, ytest. It's important that we put it in this order because that's how this function will correlate to it, and it'll put the same exact value. So if I switch ytrain and ytest, it's gonna put the wrong value in the wrong order. So make sure you guys put it in this order. And then another thing is I keep the x and y value, which just comes back from here, and I shuffle the values so that they're not in the same order. Okay, perfect. And now what we're going to do is we're going to create our linear regression model. So when you went to the libraries workshop, I'm sure that you guys learned about what specific libraries is, but when we call it, we store our linear regression model in a variable called model, and then we also do an extra step, which is fitting the X training data and reshaping it to -1 and 1. It's important that we do this step because it basically allows our features to be set up differently. And if we don't do it, you'll see that we produce an error. So once again, we store that in a variable called model, and that basically allows us to produce the model. I did write uncommon line because originally I wanted you guys to do it, but it was sort of producing an error. So next up, we're going to predict values for y, and this is called ynew. Specifically, why this is to show that when we plot our graph, we get all the different points that we need. And essentially, I just take the x train values, but you can also just use an arbitrary number of x values and put that into a variable called ynew. Essentially, this will just create new coordinates for our linear regression model and allow us to create our new graph. And now we go to plotting the graph. So first things first is we plot the actual line, which consists of x train and ynew, and that will be this line right here in blue. And second of all, I also wanted to scatter the x and y coordinates. So I see that I have the different scatter points. And over here, there's one important thing to note, that we actually see a pattern. As x and y go on, we actually see that the linear regression model fits perfectly. However, if there are a bunch of different data points scattered all over the place, this linear regression model would have trouble showing what exactly is the linear regression. And we can see that in our accuracy too. So, but just before we move on, we use plot.show to show our graph, and that's how we see this model over here. Now, we also want to check the accuracy of this model just to show us how accurate it is. This is a smaller data set, and there could be producing some error, but it's important that you still do this no matter what. So basically, I print out the string, score on testing data, and then I use the function score, which essentially just allows us to test the accuracy. So I do model.score, and then x.test, which is once again our testing data. Make sure you keep that in mind. We're going to be using our testing data, not our training data, and then our y testing data as well. And I reshape both of those, and I get an accuracy of 99%. So that is actually really great. And this is sort of what we want to look for. And we know that this set of data that we have is perfect for linear regression. But let's say that we had a score of 0.5, then we know that there's a bit of an error, and we might need to readjust either our data or the type of regression that we use. And I was just wondering if anyone has any questions about what we've done so far. Is everyone okay with what we've done so far? Can I get thumbs up? Yep. Okay, great. Perfect.
We'll take some time at the end of the session too, just for any outstanding questions.
Sounds good. Okay, perfect. So once again, just keep this in mind as you go through. This is a perfect introduction to linear regression, and it'll be very useful later on whenever you create more models of it. Okay, now let's keep going. Okay, the next slide. Okay, now let's go into let's dive deeper into regression. Obviously, we know that y = mx + b isn't the only function that exists in this world. And there's many different types of regression that follow through with this. So we have linear regression, and we also have something called polynomial regression. And with this data set, we see that it sort of arcs. And that won't exactly fit our linear regression model. If we were to do a score on this model, it might be something like 0.3 or even 0.2. But if we put in a polynomial model, that'll fit much better, and that'll give us a score that's much higher than linear regression. So just letting you know that there is a much bigger variety of regression out there than what I state here, but this is sort of an introduction, and linear regression is a very, very easy way to get started with regression. Yeah, perfect. Okay, now let's go through the different types of machine learning. So far we went through regression, and that sort of falls into a category called supervised learning. Basically, supervised learning has labeled inputs and outputs. Whatever we put into it, the model knows that there's going to be something of this input, say color or size or even like speed, and output. We get a certain output that is labeled. This is used in neural networks, regression, and classification. I bolded these three because these are the three examples that we'll be talking about today. We also have another category called unsupervised learning, and this sort of has no label on input and output. And this can be used in customer segmentation and clustering. Essentially, when we have no labels, the model itself filters it. And finally, we have reinforcement learning. So reinforcement learning is heavily used in games, where it's sort of like a reward-based learning. So if you get the answer, if you choose the right move or the right answer, you get rewarded based on it. And if you don't get rewarded based on it. So the computer knows to choose the rewards versus choosing the answers that give the rewards versus not. This is really widely used in games. So for example, a Connect 4 solver. When we choose what the right move is, we can use reinforcement learning and many different games to show what exactly is the right move. Think of the first time that you learned how to play Connect 4. I'm sure the first time you probably made a couple errors too, and it took that trial and error for you to get the right techniques to hopefully one day beat someone. And that's exactly what the computer does with reinforcement learning. Okay, now let's dive deeper into classification. So in classification, we sort of process our data into classes or groups. So classification on the left, we see that we have two different groups, green and blue. And these are sort of classified through this line separated before. We'll talk more a bit about why this line is important, and we'll also talk about why some data points are in one section some blue are in green and why some green are in blue. On the right, we also see that we have linear regression. So this is what I was talking about when I meant that some sample sets may not be adequate for linear regression, and this is one of them. We see that we have a whole bunch of points. And although there is some upward trend, it might be better to use a classifier in this case. For example, if this was apple versus oranges, the right linear regression model wouldn't exactly show us what is an apple versus what is an orange. And if we use a classification model, we can see that the green side is a green object, while the right side is a blue object. And this is sort of the difference between classification and regression. Okay, so with classification, our model divides the data using a line known as a decision boundary. And this is sort of a function. So this function splits over the two different groups. So as we go back before, we see that the line's in the middle, the green is on the left, the blue is on the right. Same thing over here. What we see with this is that this creates our two different classes. And this is how we know whether something's in one class or another. So let's say I have a coordinate that's in the bottom left. Well, I know that's part of class green. If it's in the top right, I know it's part of class blue. Another thing to note is that sometimes the machine may not be able to correctly predict what class it's in. So we see some overflow of green objects into the blue class. And that's completely okay, because this once again goes back into our scoring model. How accurate is our model versus the data that we have? Okay, perfect. And let's go through the different types of classification models. So first things first is we have k-nearest neighbors. And the way that k-nearest neighbors work is that it basically takes a data point, so green over here, and it compares it to all its neighboring data points. So as we can see, we have orange and we also have blue. It sort of detects the distance between all these points, and whatever's the shortest point is the closest class, sorry. So think about it. If you were in a section, you would go to the most closest point, and that would be your closest relation in this data set. So if you were green, you'd be closest to blue, and that's why this model has k = 3 or blue. It basically stores the training data, so it uses the training data in order to allow it to predict. So in regression, where we predicted new models, this sort of uses the training data to predict the distances between neighboring points. And once again, the distance is very important to calculate what is part of which class in classification. We have another type of model called logistic regression. And a difference to note between this and k-nearest neighbors is if we look back at k-nearest neighbors, we could also have a patch of dots in the top right and call that like yellow. So we could have multi-classes in k-nearest neighbors. But with logistic regression, we see a sort of 1 or 0, a this or that output. And that's really important to know. So in your data set, if you were looking for multiple classes, it may not be the best to use logistic regression. Instead, you'd probably use k-nearest neighbors. And there's many different types of classification models as well, but these are just the two that I'm going to talk about today. Okay, so once again, we spread our classes based on the 1 or the 0, based on the input, And whatever value it falls on, well, that's how we know what the class is. And another important thing to note is that if we're somewhere in the middle or the threshold value, there could be a small margin of error that produces the wrong output. So for example, with the blue dot going closer to the green class rather than the blue class, that might be due to error, or that might even be due to just the way how the model works. And the way that we trained it made it underfit or overfit. So once again, note that when there's a value that's in the middle, it's sometimes very easy to push it into the wrong class, and that just goes with model accuracy. Okay, so now let's walk through a classification and a k-nearest neighbor example. So this will be in the same notebook. Once again, this is also in the Zoom link, and I'll switch over to it right now. If anyone doesn't have it, just type it in the chat and we'll figure that out. Okay, so let's get started. Okay, so back to our old notebook. What we're going to do is we're going to close the model plus regression tab, and we're going to open a new tab called classification plus k-nearest neighbor. Okay. First things first, same as before, we're going to import a library. And basically this library will be different this time. Instead of linear regression, we're going to use k-nearest classifier. So this will be a KNN model. Also, this data file will be located in my Google Drive. So something from before is that I sort of created that data set, but in this one is an actual data set that I imported from a CSV file. Okay, perfect. Now, next thing, we're going to store this into a variable called fruits, and we're going to read the CSV file that's called fruit data CSV. And also, let's print out the data to sort of see what we're looking at. So I see that we have many different values which indicate what section that we're looking at. We have fruit label, which equates to a fruit name. So 1 would be apple, 2 would be mandarin. There's also a 3 and a 4. And the fruit subtype. And then we also have the mass, width, height, and color score. So one thing I'd like to ask you guys is that, do you think that all these points would be important in determining what the fruit is? So do you think that color score would be important in determining what exactly a fruit is, or which fruit it is? Does anyone want to give that a quick shot? Okay, no worries at all. So what we can do over here is that we realize that there's 3 different values that we want to look at: mass, width, and height. So color score may not matter too much because maybe there's two colors that look very, very similar. So what exactly would be the difference between them? Or maybe there's 2 fruits that may look red. So that's why we specifically chose mass, width, and height. It's very important that we stick with this and that we don't overshoot through anything else, because that may deter our accuracy score. And finally, our label will be the fruits label. So this will be a 1, 2, or 3, or 4. And later at the end, we'll convert that into apple, mandarin, I believe it's lemon, and something else. Okay, next up is our test train split. So over here, we have once again, all of our variables, and we're going to store all of our X and Y values into our test and train split. Okay, so now let's create our model. I already imported it above. I accidentally imported it again, no worries. But basically, we're going to create a KNN variable with a model of K neighbor classifier, which we imported. And we're going to fit it with our training data. Note, once again, I'm using the training data here instead of just the normal X and Y variables. And over here are all the other values that we can use within our data. Okay, now let's predict an outcome. So once again, we have mass, width, and height. And I see the mass over here with 192. So I'm going to put in a value of 20, just an arbitrary value. A width, I'm going to put in 4.3, and a height, I'm going to put in 5.5. So these are my mass, width, and height input that I'm going to put in, and I'm going to ask the model to make a decision on what it thinks it's going to be. Okay, so I'm going to store this as fruit prediction, and I'm going to print the value to see what it gives me. So the value that it gives me is 2. So over here, I see I have 1 and then 2. So 2 is mandarin. Essentially, the computer is telling me mandarin, but it's giving me the number 2 instead. So I'm going to convert this number into an actual string. And that will be, if the fruit prediction is equal to 2, I guess a mandarin. And that's exactly what it outputs. So once again, it might be a little bit hard to understand what exactly the computer is outputting. And that's why I believe that it's important that you sort of look through your data and understand what each and every value means. So if you ever want to take a deeper dive into it, you can always look up the fruit data set or even print out different values of it just to see the whole data set overall. Okay, finally, we're going to predict the accuracy on it. So once again, we're going to use the scoring model and we're going to test the data. We're going to use our testing data to predict value. And we see that we have a score of 0.5. So sometimes our score isn't up to par of what we really want, and that's completely okay. Maybe this model wasn't adequate, or maybe we didn't use enough training data. There could be many different outcomes of why your model may not work. Another thing to consider is that maybe color score was in fact a model that we could use. So if we added onto it, maybe that would change our accuracy. And maybe that's something that you can do in your free time. Okay, so that's our K and N classifier. Let's also go through another example of classification. It's going to be logistic. Okay, so over here, we're going to start off with, so this is basically like a whole class that we create. So if we look at the one before, I see that I just imported this from a sklearn module, but over here we actually created it ourselves, and that will be log regression. So you can look through all the code, and this is essentially what it goes through each and every step. But once again, it'll have two different values, a 1 or a 0. And that's very important to note. If you have multiple classes, you don't really want that. You don't really want to use this model. Okay, let's go through the data. So we're going to load a data set, and what we're going to do is we're going to store it into our y and our x and our y variables. Okay, now if we look at the data fields, this could be all the data fields within our x values. So instead of mass, height, and width, we have many more different data sets. And maybe all of these may not help out with the model. So once again, that will be just through our feature extraction. And what we can do with our feature is that we can look deeper into it. But let's just take a look at all of these, because it sounds like all of these are really important to looking at what type of cancer is this tumor is. Okay, next up we have our classifications. And also we're going to split our testing and our training data. Okay, so once again, our two outcomes are Malaysian and Malay. Okay, so now this is sort of the introduction to it. You can import the model and then you can fit the data on your own. So once again, I use fit. There should be a fit function, right? So you can call in the logistic regression .fit, put in your training data, and then finally you can test it with your training data. Your testing data, and figure out the accuracy of it. So this is another model that may be very useful to you. So make sure, I will also share this. I don't think I've shared this right now, but I will also share this later. Okay, now let's head back into our PowerPoint. Okay, now let's talk about neural networks. So neural networks are a collection of connected nodes called artificial neurons. Essentially, each of these neurons or nodes will create some sort of data, will have some sort of data, use that data like that it received from the input, process that data, and then like depending on what the process is, it can either give some data or give a 0 instead. So each signal, when each neuron sends a signal, it's a real number. So we have to remember that it's going to be sending usually a value between 0 or 1 or 1 or 0. It doesn't have to be between. And they're transformed using a nonlinear function. And these neurons are put into different layers, which allow it to take the input data, process it within hidden layers, and then finally have an output data. So let's take a look at a physical version of this. So on the left side, we have our input data with 3 different inputs. And then we have our hidden layers, which process the data through nonlinear transformation or even through other functions. And finally, we have some sort of output data that we'll get back from the computer, and we'll realize that, okay, this is what the neural network is going to give to us as an output. Okay, now these different functions are called activation functions. I'm going to talk about 3 today, but it's important to note that there's a wide variety of activation functions that you can use within your neural networks. It's important to realize this because these 3 may not be the adequate set for you, but especially one of them becomes very, very useful and very useful overall in neural networks. So first things first is we have binary step. So this is useful if you want sort of a threshold value. If you want, like, let's say you have a node that has a value of 0.5, but your threshold was 1. Okay, that node will process an output of 0 to the next node. So we know that that threshold hasn't been met. So once again, there's a threshold in this that has either 0 or whatever the threshold will be if it's met. Next up, we have sigmoid. So a sigmoid is very important because it can basically give us an output of either 0 all the way to 1. And in neural networks, this is probably one of the most widely used, especially in the hidden layers, because sometimes you want sort of an estimation or a prediction value. And that's exactly what the neural network will be doing inside its hidden layers. And then finally, we have a rectified linear unit. Basically, with a rectified linear unit, we have sort of a linear unit of our function, and then unless the value of the function of the input is 0, the function will never produce an output of 0. So every input is matched with an output unless there's a 0. So that will just be 0. Okay, great. And let's go through different types of neural networks. So there's 3 different types of neural networks: artificial, convolutional, and recurrent. With artificial, this is sort of known as a forward-fed or one-direction neural network. So input is sent through the left and then brought out through the right. With this, we see that the flow is processed like this, and this basically allows our information to be processed through the neural network once and then give us an output. Okay, next is convolutional. So convolutional, we basically give it some sort of frame or photo in this case, and it auto-filters the data, allowing it to predict its own value using features that it determined through the photo. So for example, for a cat, it may look at the stripes, it may look at the tail, it may even look at the facial structure of the cat, and it determines the output of a cat. However, for a dog, it may look at something else. For example, it may look at, once again, its facial structure and realize that it's sort of different. So these are sort of auto-filtered data that a convolutional neural network gives us. And finally, we have a recurrent neural network. So the important thing about a recurrent neural network is that it takes the input, the first input that it gets, processes a new output, and then uses that same input to process more and more output. So if I look at the sentence below, we see that what is given to us as an input, the model produces a new output, and then it reuses that to make the next word, and then finally the question mark. Okay, now one thing I'd like to mention before we move on is the training of neural networks. So in artificial neural networks, I talked about how it would be forward-fed, so going from one direction to another. But in the training of neural networks, we have to realize that it's forward-fed, and it also uses backward propagation, which means that it goes backwards and gets back the input in order to further train it more. So think of it like this. What the information goes through once, okay, there's a little bit of error, let's make a little bit of adjustments, let's go backward and train it again. So in artificial, when we produce an output, it's going to be forward-fed only, but in the training of it, we forward feed our information, but we also use backward propagation in order to make any changes to it. Okay, perfect. Now let's go to the neural network example. So once again, this will be in the notebook once again, and let's hop to it. Okay, so I'm going to close the classification one, and I'm going to open the neural network one. There's also a Keras neural network. We'll go through that after. Let's start off with the scikit one. So I'm going to import my library. That'll be sklearn, and I'm going to use a dataset called make blobs in this. So this, once again, I'm importing from the module of sklearn. Okay, next up, I'm going to store this data, and I'm also going to label the different data and then give it some colors, and then print out the output in a model plot. So these are all my data sets, and this will sort of be the data set that we're working with. So this will be what the computer sees, except in terms of it won't really see the colors, it will just see the coordinates of each and every point. Okay, next up, we want to split data. Once again, in every single example, we split the training and testing data. So make sure we do that once again. And after that, we also want to take a look at our model. So our model will be an MLP classifier. Now, this is an artificial neural network. So remember, forward-fed. And what we're basically going to do is we're going to create our neural network, and we're going to give it many constructors such as max iterations. I use max iterations equal 1,000. So when I first created this model, it had a default value of 100, but that didn't really work for me. And it said I need to up the iteration. So with the training of it, it needed to go through more iterations of it in order to create the right output. And this will sort of be dependent on the trial and error of your model. So make sure you look at all the different constructor elements that we have, and we see what each and every one of those do. Okay. And also, we also look at our hidden layer sizes. So we know that there's 6 hidden layers between the input and the output. Okay, perfect. And now let's fit our data, which is our training data. In this case, we swap data with X and labels with Y. So this is just our training X and our training Y. Okay, and then finally, let's score our model. So with all the blobs that we get, our model takes an input from our testing data and predicts what class it's going to be in, whether it's blue, yellow, green, or pink. And we see an accuracy of 92.5%. The cool thing about neural networks is that because they go through so much training, their accuracies tend to be really high if trained long. And that's a really powerful technique. So if you ever use neural networks, just remember, with the iteration and the learning process, that would help you create a much more powerful and accurate model than ever before. Okay, so that was sort of the scikit learning aspect. Now let's go through the TensorFlow and Keras neural network. So this is sort of a convolutional neural network. So this is not an artificial one anymore. And that's important to note as we go through, because all of our data, it's like if we want to use a data set that uses an artificial neural network, this may not work exactly for it. Okay, so first things first is we have our training images, our testing images, and we set that once again into images and labels. So images being the X value and labels being the Y. Okay, now sequential is so we're gonna set up our model, and then we're gonna add the different layers into it. So we have our convolutional layers, and then we also add a max pooling layers, which sort of like make the layers much more efficient. And then finally, we're also going to compile all the layers together and then fit them with the training images and testing training labels, which will eventually allow our model to be trained with the right amount of layers and output. I'm just going to let Daniel continue on with this. Daniel, you can go ahead.
Yeah, so if you can see in all the different layers, they are given an activation function similar to the ones that Gunvir was talking about earlier. As you can see, basically all of them come down to a ReLU, so that was the rectified linear unit that they were using, and this is just to give a weighting on a linear scale on all values, and then also have the option to weight something at 0. This just lets you deal with neurons that tend to give incorrect options, that you get to give them that connection a weighting of 0 so you can avoid those. And then if you scroll down a little bit and we look at the output, as you can see, this is a Keras model that works on images, which is a little more computationally expensive. And unlike the neural network that we saw with the scikit-learn model, this one actually takes a decent bit of time to run through each iteration, and then you can actually watch as the accuracy changes through every iteration that we go through. So you can see that the accuracy from the training data set starts after the first set of iterations at only about 30%, and by the time that we complete, we're at 76%. And this is just a short training period here we had for an example, but assuming that you kept training your model for significantly longer with more iterations, you can confidently assume that your accuracy would increase to a certain point.
Perfect. Thank you so much, Daniel. That was a great explanation of it. So once again, through each iteration, our neural network learns through more, and our accuracy becomes better as we go on. Okay, now let's hop back into the PowerPoint. Okay, perfect. So now that we've gone through those examples, finally we talk about improving our model. So when we improve our model, we see that sometimes there's an error that we don't exactly want. And how do we fix this? Well, we have the optimization of our model. And an optimization can just be changing the iterations to make our model much more effective at the cost of computation, obviously, using different data sets or even changing the test train split. Instead of making it 25%, 75%, it could be a different value. And we also have optimization functions. So these are actual functions that allow our model to produce and calculate our data set much more accurately and effectively. And finally, I'd like to talk about underfitting and overfitting. So with our values that we have, sometimes we put in too little or too much. And we want to make sure that we avoid this scenario and get the perfect amount of data that we have. And with our data, we want to make sure that we produce the right amount of data and use the right amount of testing and training data. So we have an equal proportion. We have a great proportion of training to testing data, where usually 75 to 25 works great. But if there's ever an accuracy model and you see that it sort of changes as you go, you can maybe adjust this to account for any underfitting or overfitting. Okay, and that should be all today. Thank you so much for coming. Do you guys have any questions for me today?
I have a question.
Yeah.
So, awesome presentation, guys, Gunvir and Daniel. Really, really in-depth. I am wondering, we spoke about 3 different types of neural networks: recurrent, convolutional, and artificial. Can we touch on the typical use cases for each of those, which is to say, like, when would you really use a convolutional neural network versus when would you use a recurrent neural network, just so everyone has a bit more clarity on the use cases?
Yeah, for sure. Okay, so let's start off with an artificial. So obviously, like, let's say that we have an equal, well, let's say we want to put in input and get a sort of like a traditional output. Our artificial neural network is sort of the base use case of it, but a convolutional neural network will basically allow us to auto filter through data. So if I give it through, if I have many different images and I want it to determine, I want my neural network to determine what exactly these images are, that's sort of a typical use case scenario in convolutional neural networks. And then finally, with our final neural networks with Recurrent, we see that word processing may be a great typical case use. So our neural network gets one word, it's like, let's say thank, and then it tries to create a new word, you. So with this, it sort of gets the word from before, creates a new word, and then continues to make a bigger and bigger sentence with the word that we have before. So if you ever texted on your iPhone and you see that it gives you information already, it gives you words that you could possibly use. Well, that's how they come up in the first place. It takes the sentence that you've already written, and it tries to predict an accurate outcome of what you may say next. So if you say how was, it might add on your day, and that's how a recurrent neural network may be used as well.
Awesome. Thank you.
No problem. Does anyone else have any other questions?
If not, we can just take a 10-minute break before we get into the final workshop of the day, which is going to be feature engineering. We'll keep an eye out on the Discord chat if you guys think of any questions in the meantime.